You think uncertainty is about not knowing something. You think it means you haven't measured carefully enough, that your instruments are crude, that with better technology or better physics you could pin the thing down. I spent my career in quantum mechanics, stood at the center of the most consequential physics of the 20th century, directed the work that split the atom and changed civilization, and I can tell you that idea is wrong at the foundation. Not slightly wrong, not wrong in the way a student gets an answer wrong on an examination, but wrong in a way that, once you see it clearly, rearranges the entire architecture of how you understand the physical world. Uncertainty, as quantum mechanics reveals it, is not a confession of ignorance. It is a statement about the nature of things, and the difference between those two ideas is the most important intellectual revolution of the 20th century, one that most people, even most educated people, have never fully absorbed. Let me take you back to where it started. When I was a young man studying at Göttingen in the mid-1920s, working under Max Born, we were in the middle of something none of us entirely understood, and the not understanding extended well beyond physics. The Weimar Republic was itself uncertain, a democracy that did not know whether it would survive the decade. The political ground beneath our feet was no more stable than the atomic ground we were trying to map, and in the seminar rooms and lecture halls, the old physics, the magnificent edifice that Newton had built and that Maxwell, Boltzmann, and the whole classical tradition had extended, was crumbling. Not because it gave wrong answers for the things it was designed to answer. Classical physics gave superb answers. It told you where planets would be a century from now and described the behavior of gases and the propagation of light with exquisite precision. The trouble was that when you turned this machinery on the very small, on the interior of the atom, it produced nonsense, and worse than nonsense, contradictions. Classical electrodynamics demanded that an electron orbiting a nucleus radiate energy continuously, which meant it had to spiral inward. Every atom in the universe should have collapsed in a fraction of a second, and yet here you are, sitting in a chair that has no business existing according to the physics of the 19th century. The world was telling us, in the clearest possible language, that something fundamental was missing from our description. Max Planck had opened the door in 1900 when he showed that energy comes in discrete packets called quanta, but even Planck recoiled from the implications. What Heisenberg accomplished in 1925, and what Schrödinger approached from a different direction in 1926 with his wave equation, was to replace the old mechanics entirely. And what Heisenberg discovered in 1927, in his uncertainty paper, was not merely a practical limitation on measurement. Let me be very precise about this, because this is where the common understanding goes astray and never recovers. Heisenberg did not discover that our instruments disturb what they measure, though they do. He did not discover that observation is intrusive, though it is. What he discovered is that certain pairs of physical quantities, position and momentum, energy and time, cannot simultaneously possess definite values. Not that we cannot know them simultaneously, but that they do not exist simultaneously as definite quantities. Hold that distinction in your mind, because everything follows from it. If I tell you that an electron is precisely here, at this exact point, then its momentum is not merely unknown to you. It is not hiding somewhere, waiting to be revealed by a better experiment, because it genuinely does not have a definite momentum. The particle does not possess a trajectory, and this is not because we are clumsy. The concept of a trajectory, a definite path through space, simply does not apply to objects at that scale. The word has lost its meaning, the same way asking what is north of the North Pole loses its meaning. Grammatically sound, physically empty. Heisenberg illustrated this with his gamma-ray microscope thought experiment, where you shine short wavelength light on a particle to find its position precisely, and the photon kicks it, randomizing its momentum. Use long wavelength light to be gentle, and you lose resolution. You might think this is about the clumsiness of the probe, but here is the thing most people miss entirely. The gamma-ray microscope is pedagogically useful, but it misleads you into thinking the uncertainty principle is about disturbance when it is not. The uncertainty relations follow from the mathematics of quantum mechanics itself, from the wave function, from the fact that position and momentum are represented by operators that do not commute. The order in which you apply them matters. Measure position first and then momentum, and you get a different result than measuring momentum first and then position. This non-commutativity sits at the mathematical heart of the Heisenberg uncertainty principle, and it has nothing whatsoever to do with bumping a particle with a photon. It describes the logical structure of the theory itself. what it means to be a physical quantity in a quantum world. You can see this most starkly in the double-slit experiment. Send electrons one at a time through two narrow slits, and they build up an interference pattern on the far screen, a pattern that only makes sense if each electron somehow passed through both slits, behaving as a wave. Place a detector at the slits to determine which one the electron actually passes through, and the interference pattern vanishes. The electron behaves as a particle, and you cannot see both behaviors at once, because the experimental arrangement that reveals one aspect necessarily destroys the other. This is exactly what Niels Bohr grasped and articulated as the principle of complementarity, the philosophical foundation of what came to be called the Copenhagen interpretation. Bohr recognized that the wave description and the particle description are not competing theories, one of which must be right. They are complementary descriptions, each complete within its own experimental context, and yet they cannot be applied simultaneously. This is not a limitation of our cleverness, but a feature of reality, and it struck me even as a young physicist that this principle extended far beyond the laboratory. Let me stay with the physics a moment longer, though, because the implications run deeper than most people realize. Think about what this means for determinism. In the classical world of Newton and Laplace, if you knew the position and momentum of every particle in the universe at one instant, you could in principle predict the entire future and reconstruct the entire past. Laplace's demon, the name given to an intelligence vast enough to hold all that information, would find nothing uncertain, nothing open. The future would be as fixed and inevitable as the past. That picture is magnificent, and it is wrong. Not because the calculation would be too difficult, not because the initial conditions could never be known with sufficient accuracy, but because the initial conditions in the quantum sense do not exist as definite quantities to be known. The universe does not have a state of the kind Laplace imagined, and the very concept is inapplicable. And here is the beautiful part, the part that should restructure how you think about physical law. None of this makes the world lawless. Quantum mechanics is a theory of extraordinary, almost unbelievable precision. Quantum electrodynamics predicts the electron's magnetic moment to an accuracy of 1 part in 10 billion, making it the most precisely verified prediction in the history of science. It gives you the energy levels of hydrogen with a precision unmatched by any other physical theory. What it predicts, though, are probabilities, not because the theory is incomplete, but because probabilities are what there is to predict. The individual outcome of a single measurement is not determined by anything. It is irreducibly random, and the universe, at its most fundamental level, does not follow a script. Einstein could never accept this. In 1935, he published a paper with Podolsky and Rosen, the EPR paradox, arguing that quantum mechanics must be missing something. If two particles are entangled, measuring one seems to instantly determine the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance and took it as proof that the particles must have carried hidden definite values all along, that quantum mechanics was merely an incomplete description of a deeper, deterministic reality. Bohr's response went beyond the famous quip about not telling God what to do. Bohr argued that you cannot speak about the properties of a particle independent of the experimental context in which those properties are revealed. The EPR argument assumed the particles have definite states before measurement, and complementarity denies precisely that assumption. For decades, this looked like a philosophical stalemate, and that changed when John Bell proved a remarkable theorem in 1964. Bell showed that any theory based on local hidden variables, the kind Einstein wanted, must obey certain statistical inequalities, and quantum mechanics predicts violations of those inequalities. When the experiments were finally performed by Alain Aspect and others in the 1980s, nature sided with Bohr. The violations were real, which meant no local hidden variable theory can reproduce what quantum mechanics predicts and what experiments confirm. The randomness is not a gap in our knowledge. It is fundamental. And coming to terms with that, truly coming to terms with it, not just saying the words, but feeling the ground shift beneath you, that is one of the great intellectual experiences available to a human being. Let me push this further, because when I directed the work of the Manhattan Project at Los Alamos, these were not abstractions. They were engineering constraints. The nuclear reactions, the critical mass calculations, the behavior of neutrons in fissile uranium and plutonium, all of it was quantum mechanical. We could not predict when any individual nucleus would undergo fission. We could only calculate the probability, and yet from billions upon billions of these individually unpredictable events, we could calculate the aggregate behavior of the device with remarkable precision. When we gathered before dawn on July 16th, 1945, at the Trinity test site, there was genuine uncertainty, not just quantum uncertainty, but human uncertainty. The uncertainty of whether our calculations would hold, whether the implosion design would work, whether Edward Teller's worry about igniting the atmosphere had truly been laid to rest. The physicists were taking bets on the yield, and Enrico Fermi was offering odds on whether the bomb would ignite the atmosphere and destroy only New Mexico or the entire world. Fermi was being characteristically droll, but beneath the humor sat the raw fact that we did not know. We had probabilities, not certainties. The bomb worked, the physics held, and what the physics told us was this: each individual event is fundamentally uncertain, while the aggregate is statistically exact. Certainty emerging from uncertainty, pattern from randomness, the predictable from the unpredictable, not approximately, but exactly. The statistical laws are precise. I do not think it was a coincidence that this revolution in physics coincided with Claude Shannon's formalization of information theory in 1948. Some of the finest mathematical minds at Los Alamos, people who lived and breathed probability, went on to shape the theory of communication and computation. The uncertainty in the atom and the entropy in a message are, in a deep mathematical sense, the same uncertainty. Both measure the space of what is possible but not yet determined, and both tell you that information, real and irreducible information, exists only where there is genuine unpredictability. There is a further dimension to this that I thought about for the rest of my life, and it connects to something much larger than physics. Bohr believed, and I came to share this belief and tried to articulate it in my Reith lectures for the BBC in 1953, that complementarity is not merely a feature of quantum mechanics, it is a feature of knowledge itself. In human life, we encounter situations where two descriptions, two ways of seeing, are each valid and yet cannot be held at the same time. Justice and mercy, freedom and order, the life of contemplation and the life of action. These are not contradictions to be resolved by choosing one side. They are complementarities to be lived with, and the attempt to reduce one to the other always impoverishes understanding. I had long found in the Bhagavad Gita a resonance with this insight, the counsel that one must act, must commit fully to action, without attachment to the fruit of the action. That is not resignation, but the deepest form of engagement with a world that does not guarantee outcomes. Arjuna on the battlefield, compelled to act in the face of irreducible uncertainty about consequences, felt to me after the war, after Trinity, after Hiroshima and Nagasaki, not like ancient mythology, but like the most precise description of the human condition I had ever encountered. The sciences and the humanities, I argued then and believe now, are not rivals but complementary modes of understanding, each revealing what the other cannot. A physicist who knows nothing of poetry is impoverished, and a poet who knows nothing of the physical world is building on sand. Quantum mechanics did not merely give us transistors and lasers and nuclear energy. It taught us something about the structure of knowledge itself, that there are limits to what can be simultaneously known, and those limits are not failures of nerve or intelligence. They are features of reality as fundamental as the speed of light. This is what everyone gets wrong about uncertainty. People treat it as an obstacle, something standing between them and the truth, when it is the truth. It may be the deepest truth the 20th century produced. The universe is not a clockwork mechanism grinding out a predetermined future, but something far more subtle and far more open. At every moment, at the scale of every atom, there is genuine novelty and genuine indeterminacy. The future is not written, not because we cannot read it, but because it has not yet been composed. The authoritarian mind cannot endure this. It demands final answers, fixed truths, permanent certainties, and nature refuses to provide them. The most fundamental theory we possess, tested to 10 decimal places and confirmed by every experiment ever devised, tells us that absolute certainty is not available, not because we are weak, but because the world is richer than any single description can capture. And the open society, the society that lives with uncertainty rather than fleeing from it, that tolerates ambiguity and values the question as much as the answer, that society is the one most in harmony with what the atoms themselves have taught us. I have said that the physicists have known sin, but I have also come to see that we discovered something else, something that redeems the knowledge even as it terrifies. Uncertainty is not the absence of knowledge, but the presence of possibility, not a veil drawn across reality, but the very texture of reality. And learning to live inside that, to act decisively, to commit yourself fully in a world that is genuinely open, that is not a compromise with ignorance. That is the human condition, seen clearly, perhaps for the first time, in the light of what the atoms have taught us.